Hello, my name is Sonia, and today I'll be showing how resting membrane potential and action potential work. So here is my little cardboard hand that I use. So this is going to be used in the demonstration. As you can see, it's curling and moving. And if we see up close, this is what happens in the inside. Okay, to start off the video, I'm going to begin by talking about the resting membrane potential. And so basically, it's the voltage difference across cells at rest, with those values being negative 70 millivolts to around negative 90 millivolts. And as we look at this membrane, we can see that 3 Na plus sodiums come out and 2 potassiums come in. Because of this, there are smaller amounts of sodium inside the cell than potassium, which has higher amounts. On the right side here, we have an abundance of leaky potassium channels. With leaky potassium channels, potassium basically leaks from high to low, so with high concentrations from the inside, it goes to the outside. Because there's anions connected to potassium, this charge cannot leave the cell, so when potassium leaves, the negative charge is staying, and so it leaves the inside of the cell more negative. That's why you can see in the example, the cell goes from negative 5 millivolts to about negative 90 millivolts just because of these leaky potassium channels. So on the bottom left here, we have leaky sodium channels, and if we follow the rule of high to low, we know that the high amounts of sodium on the outside will leak into the cell to low concentrations of it. And basically, potassium is more permeable than sodium, so that's why when sodium comes in, there's not much of an effect. So voltage only changes from negative 90 millivolts to negative 70 millivolts. So this ultimately explains the voltage difference and the resting membrane potential. So next we have action potential. Here we basically move from resting membrane potential to threshold potential. And the voltage difference in this is from negative 70 millivolts to negative 55 millivolts. This is done by the gradient potential, and the action potential initially occurs in the axon helix, which is the trigger of where everything occurs. At the threshold potential at negative 55 millivolts, an influx of sodium rushes into the cell because activation channels have opened due to the fact that we are at negative 55 millivolts. Because positive sodium rushes in, this increases the millivolts from negative 55 millivolts to a positive 30 millivolts. At 30 millivolts, inactivation gates close and more sodium rushes in. The rest of the activation channels will begin to open and there will be more sodium rushing in. And basically, this is a depolarization wave from the dendrites down to the axon terminal. Eventually, at 30 millivolts, the calcium channel will open and an influx of calcium will rush in. And because of this, they attach to vesicles, and these vesicles will attach to the terminal end of the neuron. And when this happens, neurotransmitters are eventually released to the postsynaptic cell across. Ultimately, this action potential carries out motor functions and enables the hand in the video to curl its fingers.